So hey, everyone. My name is Guy. I'm a PhD student here at EPFL. Yeah, let's, I guess we can start. Today we're going to talk about the third chapter of Ale's and Elon's book about constructing non-interactive arguments in the random oracle model. And this is kind of going to be a recap of whatever we did 2 weeks ago with Christian. So back then we were doing non-interactive arguments from Sigma protocols, and now we are going to do it from IP. And just looking at the content of this chapter, so we're going to focus mostly on the first two parts of the chapter, which are mostly definitional, but I feel that if you understand them, the rest is going to be some additional flavors, and it's going to be pretty easy to understand. We're not going to really cover much about the optimization or the additional security definitions, but fine, I guess as long as we have the main ideas in place, we should be good. So, okay, any question about the program, more or less? Okay, so let's just start. So proofs are pretty ubiquitous in computer science, in particular in theoretical computer science, and I assume most of you have heard what they are, and if you haven't, you've probably heard the name Sumcheck, which is the most well-known example of an interactive proof. And so in terms of definition, an interactive proof is a tuple of two algorithms, right? So we have an algorithm for prover and an algorithm for the verifier. So let's look at this diagram here. I wrote basically all of the terminology that we need here. So like I said, we have the two randomized algorithms. We have the prover and the verifier. We have some instance, that's what the prover and the verifier are going to be talking about. And we have a witness as well. So you can think of it like the instance being like a program you want to run, and the witness being the intermediate steps. So you can actually prove to the verifier that you did the calculation according to some program, which is the instance. So in terms of terminology, the number of fronts is going to be k, and this is going to be consistent throughout the chapter, and I guess also the rest of the book. The prover messages are going to be denoted by alpha. The verifier messages are going to be denoted by rho, which is kind of like why this choice of letters. So I don't know about the alpha, but for the rhos, we're going to be mostly talking about what's known as public coin interactive proofs, which I'll define shortly. But so the verifier messages are just going to be some random bits. So rho stands for random. Okay, so a round is going to be a set of two interactions, shall we call it that? So the prover is going to send a message, the verifier is going to respond, and we are going to call these two messages a round. Okay, some more definitions. The interactive proof is going to be given for some relation, right? So we have a relation that is supposed to define us a language, right? For example, if you know about theory of computer science, so maybe X is going to be a sat formula, and W is going to be an assignment to the variables of the formula, and the language is going to be sat, right? So like every instance that has a satisfying assignment such that the relation contains both of them. Okay, so finally, after the interaction,
can I put that another way? This idea of relation. So in the case you just gave, right? So X, we have a formula. X is that formula. We want to know whether the formula is satisfiable or not. To show that it's satisfiable, we give a witness, that witness being the set of assignments to the variables in that formula. And so in this interactive protocol, the goal is for the prover to show that X has a satisfying assignment, and they do that by showing the existence of a W.
Yes. So actually, like, you can think about many flavors for that, right? So a trivial thing that the prover can do is just send W to the verifier, right? And maybe in terms of the size of it, you just don't want that to happen. So maybe for a SAT formula, it's not that problematic. But if you want to, I don't know, prove to the verifier that you did a very long computation, maybe it's not the best thing to just output all of the steps you did in the computation. So you would want to do something more interactive that might be able to convince the verifier just with less bits communicated. Does it make sense?
Yeah, thanks.
Okay, great. So now for interactive proofs, we have two important definitions. The first one is completeness, and here we are talking about perfect completeness. So what we want to say is, I want to say that if X is in the language that is described by this IP, the verifier is going to accept, and we want it to accept always, right? So we call it a perfect completeness to denote that. So in particular, we are going to be talking most of the time about this definition, right? This notation right here. This is going to be the random bit of decision for the verifier. So the prover and the verifier interacted. The prover has X, is the instance, and the witness. The verifier has just the instance, and they interact. Remember, they are both randomized algorithms, so this kind of so their interaction is randomized, and eventually the decision bit that the verifier outputs is also a random bit. So we are going to be seeing this notation a lot, and this is, by the way, true for interactive protocols in general throughout the book. Eventually, we'll get to more complicated terminology that uses IOPs and so on, and we use that to denote the decision bit. Good. So basically, what we want to say that if X and W are in the relation, the probability over the randomness of the prover and the verifier, the probability that the decision bit is 1 is 1. So we call this perfect completeness. Sometimes people define like this one is replaced with some other probability, but in this book we are mostly interested with the probability being 1. That is perfect completeness. Okay, so the next definition, which is going to be very important for us, is the definition of soundness. And the definition of soundness means that for every X which is not in the language, and for every malicious prover strategy, right? Because X is not in the language, so like there shouldn't be a way for the prover and the verifier to interact, and the verifier would say that X is in the language, right? This is by design. We want it not to happen by much, and quantify this our desire. We actually use the soundness definition, and we are saying that the probability that the prover and the verifier interact and the verifier decision bit is 1. And notice here, by the way, compared to this, you don't have X and W here because it's a malicious prover, right? Like there is no witness, so it doesn't really matter. Okay, so we want to say that the probability that this thing is 1 is bounded by some epsilon. Okay, so we want it to be small. Any questions about the definition of completeness and soundness? Okay, so I assume many of you have seen it, and it's like Giacomo and Christian also mentioned this, but it's important to mention. And the most important thing in terms of what's new for IPs is this notation, right? Like we have some interaction, and we get some bit after this interaction. Okay. Some additional efficiency measures that we need to maybe care about. The first one is the round complexity. So we want to say that the round complexity shouldn't be much, right? Like if we design a very good interactive proof, we don't want the verifier to have like a round complexity, which is the size of the witness, right? So round complexity is an important measure. And like I said, a round contains two messages, one from the prover and the one from the verifier. The second one is communication complexity. Same goes for communication complexity in terms of us not wanting the verifier to be able to extract the witness in full. We don't want the verifier to read the witness so most of the time. But that is not by definition required in IPs. But I'm just like preparing you for like what we would eventually want from our IPs to satisfy. And finally, we have some consideration for the prover runtime and the verifier runtime. If you're from the ZK community, I guess you know that we care about prover runtime being linear. Yeah, so there is also some consideration in many of the well-known protocols, such as like vanilla SumCheck that you read about in complexity books. That's actually not the case. So for SumCheck, the prover is not efficient. Okay, so any questions before I go to the definition of public coin interactive proofs?
I don't see any in chat, but just reminder that to folks here that you are welcome to sort of pop in with questions. You don't need to type them in chat. If you can unmute yourself and ask if you have questions.
Yeah. And I encourage you to do it. I mean, maybe these definitions are not super difficult, but they will become more and more difficult as we continue.
And everything builds on top of each other. So if you don't understand these definitions now, you'll have a bad time later. Sure,
that is true. Okay, so so far we were talking about IPs in general, and a very important class of IPs is the class of public coin IPs. And what is public coin IP? So a public coin IP is an IP in which basically the verifier messages are just its randomness. So remember, I said that the verifier and the prover are randomized algorithms, right? So they have some randomness that they own. And in public coin interactive proof, basically what happens is that all of the messages from the verifier are going to be the verifier own random coins, right? And we denote this by that. So basically, the decision bit of the verifier is fully determined by alphas, the prover messages, and its randomness that it shares with the prover, and of course the instance. So notice that there is no other randomness in the decision of the verifier, and I don't know if it looks weird or not to you, but in some sense it shouldn't look weird to you, because in many protocols that we know and love, like think of Fry, for example, the verifier is just all about trying to catch the prover on a random point, right? So the verifier is going to send some random challenge, and because it's random, the prover cannot prepare for it. So the fact that the verifier messages are just random bits shouldn't be so surprising to us. And apparently it captures a lot of the power of interactive proofs just with this definition of public coin. And from now on, all of our interactive proofs are going to be public coin. And in particular, it matters much when we talk about the Fiat-Shamir transformation that we'll see next. We can't really talk about that if the verifier has some randomness that it doesn't share with the prover. Because eventually we would want to replace the randomness by some random oracle, right? So this is also why we think about public coin interactive proofs. And yeah, so it's like a very important class of interactive proofs, and in particular, this is going to be the only one that is interesting for us. I think also for the rest of the book.
I have a question. About the randomness, the verifier needs to know the domain, like where they pick the randomness from. Is it like the normal domain, or is it an extension, or what is it?
Yeah, so you can assume the prover and the verifier know what they're expecting, and so maybe like interactive proofs is kind of like the rules of the game. So like when they interact according to some rules, which are the rules of the interactive proof. Right, and in this the definition of the interactive proof, you have the setup, right? And in that setup, they should know what they are supposed to send each other, and in particular, they should know what they're talking about, because otherwise, how the verifier can expect to be convinced, and how can the prover expect to convince the verifier? So we are going to assume that these things are known to both sides. Any other questions? Okay, so now we're going to talk about a couple of definitions related to properties we want from the IP. Okay, and an important property that we want from an IP is to have what we call knowledge soundness. Right. So if you remember before, the definition of soundness basically said that if X and W are not in the relation, that is, there is no W such that X is in the language, the verifier should reject. So this bit of decision should be 0. But how can we quantify the probability that the verifier? How can we quantify the fact that we want that if the prover accepts, it's because there exists a witness, right? We want to be able to say that acceptance from the verifier, means that there was a witness in mind. So like the prover cannot convince the verifier without having some witness. And for that, we're going to define the notion of extractor, right? And this extractor is going to be going to have access to an interaction transcript, and it's going to have a black box access to the prover, right? Because if it didn't have it, if it wasn't black box, maybe the extractor could see the witness, right? So for that, for the specific definition of an extractor algorithm, let's define the failure probability of some prover strategy. Okay, so for a specific prover, this prover, which is deterministic, so there is nothing crazy going around. In particular, it's not related to the witness or instance. You can think of it as hardwired if you want. Then the failure probability is this. Okay, so the probability that the prover and the verifier interact and get the decision bit is 0. Then we can define the extractor algorithm as follows. So we're going to define the extractor such that when you feed it the instance alphas, which are the prover messages, rows, which are the verifier randomness, and a black box access to the prover, we're going to be able to extract a witness. Right? And we want to say that the probability that X that you extracted and the witness, X that you get and the witness that you extracted, probability that they are not in the language, while you were able to convince the prover, the verifier. So like we have this B here, right? This B means that the prover and the verifier interacted, and from the interaction you get some bit. In this case, it's B. So in other words, what we are saying here is that the probability that you are able to convince the verifier, but W that the extractor outputs is not in the relation, so like XW is not in the relation, this probability is small. Okay, and it's going to be related to the success probability or the failure probability, depends on how you want to look at it, of the prover that we are looking at. Okay. Moreover, we want to say that this extractor runs in expected time. It is dependent on the failure probability of the prover and the runtime of the prover, because eventually the extractor might want to rewind or do crazy things with the black box access that it has. So it needs to run the prover. So yeah, so this is what we want to say about extractor. And let me just recap this definition. And I know it's a bit technical, but the most important thing to remember is that we want to have some algorithm, okay, this denoted by E, that if the prover and the verifier interacted and the verifier accepts, so it outputs this B, which is 1, there should be an extractor algorithm that outputs W such that X and W are in the language. So we want to say that the probability that this W is not in the language is small. So it's upper bounded by some probability. Does it make sense? Do you have questions on this definition? Have you seen this previously, like a definition of extractors? I think maybe Christian mentioned it. Okay, I'm going to assume it's clear. We are not going to talk so much about this definition. It's important to note that all of the definitions, all of the constructions that we are going to see soon have this property. Okay. So yeah, let me just mention that there are a lot of flavors of extractors, and they're used for multiple different use cases. It's really an active research area, and they give you better and better knowledge soundness guarantees. But let me just mention this straight line extractor definition, in which the algorithm just receives the input and the prover messages, but not the verifier messages or the access to the prover. So the extractor basically gets almost nothing, and from the interaction from just the prover messages of an accepting transcript, should be able to output the witness. So that would be a very strong definition of knowledge extraction. So that just by having the prover messages of an accepting transcript, you are able to extract accepting witness. So this is something that is usually very desirable to have, like this straight line extraction, which will come up in future lectures. Okay, another very important notion for interactive proofs is the notion of zero knowledge. We are in a ZK hack session now, right? So I assume many of you know what is zero knowledge, but let me just say that we are eventually working under the assumption that everything that is efficiently computable is free, right? So if we see something that we could have done ourselves, we are going to say that we learned nothing. So basically, what the definition of zero knowledge says the following: the prover and the verifier interact, and they have some transcript. And in the language of zero knowledge, in the lingo of zero knowledge, we're going to call this transcript a view. Okay, so this view is going to be determined by the prover, the verifier, the instance, and the witness. And we want to say that an interactive proof is zero knowledge if that view of a true prover and true verifier interacting with the presence of a witness. Notice here that there is a witness here. So like X is in the language and we have a witness for it. We want to be able to say that there exists a polynomial time algorithm, probabilistic maybe, that actually outputs transcripts such that the output of this simulator and the view of the real interaction are going to be statistically close. And you can say a lot of things about whether you want this to be statistical, whether you want the distribution to be actually the same or like computationally distinguishable. Yeah, so that's the definition of zero knowledge. Very briefly, but I assume most of you have seen it before. Do you have any questions about that definition, or if you haven't seen it before, do you have any questions about that? Okay, so far we have set the ground for the basic definitions of IP, right? We defined what is soundness, we defined completeness, soundness, some terminology about number of rounds and so on, and we said something about the knowledge soundness, which is also an important property that we want, and zero knowledge. Now we're going to get to the main definition of this session, which is going to be a state restoration function, state restoration soundness. Sorry. So the quickest way I found how to explain it is that a state restoration soundness is a property of a public coin IP that quantify how much the prover can learn about random function that the verifier has. And it kind of plays a game against this random function to be able to fool the verifier eventually. So I don't know if it makes it less or more cryptic, but I hope that once we're done with this explanation, it will be clear. So, like I said, we are talking about public coin IPs, right? So the verifier only has only shares its randomness, right? So maybe you can say something like, okay, let's assume that the verifier has some random function that it just queries on something and then sends the output of this random function to the prover, because this is essentially what is happening, right? Because the verifier just shared its randomness. So now we can say, okay, let's say that it's not just a random function that the verifier has by itself, but maybe it's some random function that the prover can interact with. Okay? And this kind of motivates us to think about random oracles. But in any case, if the prover can, I don't know, ask a lot of things from this function, maybe he has a better chance of fooling the verifier. So this kind of intuition is what is being formalized in this notion of state restoration soundness. So this notion is defined using what is known as a state restoration game tree. Okay, so this tree is going to be defined as follows. So what we are going to have is that at every node of this tree, we're going to have a partial transcript. And how do the partial transcript look like? They contain the instance, this is X. They contain the prover messages at some point, right? We have the number of levels in this tree are going to be correlated with the number of rounds. And we're going to have some solve parameters. We're going to add these solve parameters because when we query a random function, we maybe want it to be unpredictable, so we are adding these solves for good measure. And it's going to be useful when we want some more security properties from our constructions. So what the prover is going to be doing is that the prover is going to try and traverse this tree, and eventually it gets to the leaf. And what is in the leaf? The leaf contains a complete transcript. So it contains X, which is the input, and all of the prover messages along k rounds of interaction, as well as the salts for k rounds of interaction. Okay, and the goal of the prover would be to output a complete transcript, much like we see here, such that the verifier would accept on this complete transcript. Okay, so let's look at the definition of. So did you say something? Okay, so let's look at the formal definition of state restoration soundness. So, state restoration game for interactive proof with salt size S and random functions. Remember, this notation means that we sample a random function for every round. We have k rounds, and the length of the input is going to be R. The state restoration proof is going to be doing the following. So the state restoration basically runs a state restoration prover, which is an object that we don't really care how it behaves, but what we care about is what's the input and output interface of this prover, and moreover, how much is it able to fool the verifier. So we're going to repeat the following until this object decides to exit the loop. And what are we going to do? The prover is going to output some partial transcript, right? So it has X, it has alphas, which are the prover messages according to some, until some round, and sigmas, which are salts. Then we are, as the game, are going to return the random function value on X, the input, and the prover messages and the salts. We're going to send it to that box of state restoration prover, and the prover is just going to continue. So basically, what is happening here? The prover is trying to learn something about the random function. So you can think of it like at every edge, the prover gets the value of the random function on that input, right? So like, let's say the prover wants to know what is the random function applied to that input. It queries that, right? In this definition, the prover outputs this query, and it receives back a randomness. So like you can imagine that here there is actually some row, which is the random function applied to that. Okay. So the prover is basically going to try to learn something about the random function, and we can assume that the prover is kind of powerful, right? Because it doesn't just guesses the entire transcript or whatever. It can traverse some interaction tree and try even to learn, like, let's say that the prover queried that and that. So maybe the prover learned something about correlated statements, or like correlated the transcript, right? And eventually the prover outputs a complete transcript. Okay, as like the prover outputs that, but eventually the game is going to output the randomness of the verifier, which is just applying the random function to every intermediate step of that computation. Okay. We moreover say that this prover is a T-move prover if it can just query T edges along this tree, right? So if the prover is all-powerful, right, you can discover the entire state restoration tree, and by that gain information about the full information about the random function, right? And we don't want that to happen because, well, if the prover can break the random function and learn it, of course it can fool the verifier, because the verifier is no longer randomized in a sense. So what we want to say is that we want to say that this thing is restricted by doing just T moves along this game tree that we saw before, and we're going to say that an IP has state restoration soundness if for every salt site and for every move budget T, T-move malicious IP state restoration prover and some bound, right? Like we have some bound on the instance side, that doesn't really matter. What we want to say is this. Let's say that we start by picking out random functions for every round of interaction. And we want to say that this game that uses that receives the salt, the random functions, and the prover, whatever it may be, we want to say that this game outputs this tuple here, in which we have the instance, the prover messages, the salts, and the randomness, like I said before. We want to say that the probability that the verifier accepts this thing, so like it is indeed a correct execution, a valid execution of the interactive proof between the prover and the verifier on instance X. Notice also that X is not fixed here, so like the game is free to choose X adaptively. The probability that this happens is bounded by some parameter, which is going to be the state restoration soundness. So, in a sense, this definition, this complicated definition, actually says something very simple. The prover has T moves to try to learn something about the random functions, right? After these T rounds, the prover should the T moves. The prover should output something about what he learned. He should output an entire transcript. And we want to quantify how much did the prover learn, and we want to say that it's not much. So this is going to be bounded, upper bounded, by this state restoration soundness. In some sense, this definition perfectly models what we expect when we talk about PHME transformation, right? We're going to see it in a couple of minutes, but it should feel very natural, because this is exactly what happens in the PHME transformation, right? The prover can query random oracle several times on maybe connected instances. When I mean connected instances, I mean, for example, you are asking this as this edge and this edge, right? And because you have the value of the edges so far, like maybe you get something by asking this path and that path. Like, I don't know, maybe that's a good strategy to learn anything about the function. So basically, it should feel very similar to what security guarantee we actually hope to achieve for the PHME transformation. So it would be good to stop here and ask if you have any question. I assume you have many, but yeah, let me know if you have any questions. Okay, so I'm going to continue. I encourage you to read this definition again, and also that definition here. I wanted to think about the syntax of what is actually going on here. So at every round of this game, the prover is going to output something that looks like this, and it's going to receive something that looks like the random function applied to whatever the prover outputs. And eventually, we are going to output a full transcript. Okay. This thing is good to keep in mind, because eventually we are going to be able to use this input and output to argue about what happens when we actually convert something to the by using the PHME transformation. Okay, so maybe let's. I'll just skip about the notion of state restoration soundness error, but it actually means something very similar to what we've seen before. But let me just skip it for now. I want to say something. I want to emphasize the differences between that notion of soundness, of state restoration soundness, and the usual definition of soundness. And for that, we're going to actually see that the state restoration function is not really tightly related to the definition of usual soundness. Okay, so we're going to see that the state restoration function is, on the one hand, an upper bound it's lower bounded, sorry, by t times k, t divided by k times the original soundness error of the interactive proof. So like, remember, t is the number of steps the prover can do in the state restoration game. K is the number of rounds, and we want to say that it's roughly bounded by that, lower bounded, which is maybe expected. Like it's not too bad. What is bad is this thing here, right? So the state restoration soundness is bounded by t plus k choose k, the usual soundness, right? So if your interactive proof had amazing soundness, but it was constant, it might not be so good, or in terms of state restoration function soundness. Sorry, because we have this huge exponential term here, right? So this is roughly t to the k. So it kind of says that if you want some meaningful state restoration soundness for your construction, your IP better have like super small soundness. Or alternatively, you can actually just go about proving the state restoration of your construction instead of like going through this IP. Because what we are basically saying here is that the transformation from the state restoration function and the soundness, the soundness of the IP are actually not super correlated. So we usually don't go about proving state restoration by this kind of black box upper bound, because it's just quite bad. And for that, I want to emphasize this this proof technique that we won't be able to go through all of the proofs in this chapter, but mostly when you want to do this kind of proof, you're going to try to construct one prover using the other prover. Okay, so for the lower bound, so now we want to say that the soundness error, the state restoration soundness error, is lower bounded by something that is roughly t over k times the original IP soundness. What we are going to say is basically we have a budget of t moves, right? Because we are saying that our state restoration prover is a t move prover. So let's just run t over k full instances of the IP, right? Each instance of the IP contains k rounds. So let's just do complete executions of these. And for each of them, we get the error of epsilon IP, right? So we can kind of say that the soundness error is at least that. That should intuitively make sense, right? And the reason it makes sense is that the soundness error should tell you how much you're going to be convinced, even though you're not supposed to be convinced, right? And if your t here is so large that you can basically discover so much of the execution tree, it makes sense that the lower bound on the state restoration soundness is going to be very big, so that your state restoration cannot be super small if you can read a lot from the random function. Does it make sense? Do you have any questions about this argument here? Okay, so let me just repeat the idea. The idea is that we are using the state restoration function, state restoration prover, in order to prove something. We are going to use the IP prover to construct a state restoration prover. So we are going to use the IP prover to construct a strategy for the state restoration prover. And the upper bound, which shows that the state restoration soundness is upper bounded by t to the k times the original soundness, is doing something very similar, right? So we're going to construct a prover, an IP prover, that uses the state restoration prover. And the way we are going to do it is, I don't want to get too much into the detail because it's a bit of a tricky idea that one has to think about here. But eventually, the state restoration prover makes a lot of queries, right? And what the IP prover can do is it can guess which queries are going to be the one that the state restoration prover finally decides to output, right? We can assume without loss of generality that we can increase the budget of queries so that there is actually such a path. So like there is actually such path, meaning that we maybe need to have like more k queries. It doesn't really matter. So the probability that the IP prover actually chooses correctly the path that is going to be outputs of the state restoration game is going to be this one. And the probability that the state restoration game wins is this. So like we kind of get that the state restoration times 1 over t plus k, which is k to the minus 1, is the soundness of the IP. And then we just, this immediately implies that bound. So I didn't go through that, but I just want to mention that those two bounds are actually tight. Okay. Any questions about this? The two bounds that I just discussed? Okay, so the most important thing to remember is that state restoration soundness is not equal to the IP soundness, and moreover, there is quite a big gap between the state restoration soundness and the IP soundness. So when we think about the state restoration soundness, it's better to prove that our construction is just has this state restoration function soundness as is, not go through this transformation. Okay, so I see that we don't have a lot of times, but just let me show you the construction of transforming interactive proofs into an argument. Okay, this uses the Fiat-Shamir transformation, and also you might see why we did all the hard work of defining state restoration soundness the way we did, because this construction actually perfectly models the state restoration soundness. So we're not going to go through these proofs, but actually the soundness of this construction is exactly the soundness of the state restoration function of the underlying the state restoration soundness of the underlying IP. So how would you go about applying the Fiat-Shamir transformation on the IP? So the prover IP is going to be used by this argument IP. So like when you have this fancy and P and V, those denote the argument prover and verifier. And the fancy prover and the fancy verifier are going to use as subroutines, the IP prover and the IP verifier. Okay, so what is the IP prover going to do? The IP prover is going to send its first message, then it's going to look at the first random function, right? If you remember in the state restoration game, every round has its random function, and now we denote this function by f. So we're going to feed this function with x, the prover message, and some salt. Afterwards, we're going to output that as the response from the verifier. And we're going to continue, basically. So now, for the next prover message, we're going to feed the next random function with x, the messages of the prover so far, so that the prover kind of commits to all of the previous messages, and again, and cannot just start from like the middle message, for example. And of course, the salt so far. And eventually, we're just going to continue, and we're going to output a proof, which is going to be the prover messages plus the salt so far. And we're going to send that to the verifier. And the verifier can, because the verifier, of course, has access to the function, the verifier can recreate the rows. Because it's a public coin interactive proof, decision bit of this verifier is fully determined by the instance, the prover messages, and the randomness of the verifier, which now is going to be the randomness that was constructed using these random functions. So this should look very similar to the definition of state restoration soundness, in which basically the prover, if you look at this prover, right, like this amazing prover that we have here, this prover, what should we expect from it, right? This prover should learn something about the random function. And the way it's going to learn something about random function is by querying it a bunch. And what it's going to query the random function on queries that look exactly like that, right? That have the prover messages so far and some
drinking
salt.
in my favorite cup.
And eventually the prover wants to win, so it outputs some complete transcript. If we go back to the definition of state
I was
restoration
reading some
soundness,
articles on ZK, very interesting.
we can actually see
But
that
since you guys are here,
this is perfectly modeled by
number 3.
By this game. So like this game captures exactly what it means for a prover to cheat in the Fiat-Shamir transformed IP. So like in the non-interactive argument that is generated by this IP. Any questions about that? Okay, so how much time do we have? You guys?
I think none, because we're at the hour, and I think the DK hack event is starting now. So I think the answer is none.
Oh, okay, so I'll just say that this construction could be made more efficient. This is the topic of chapter 15. This construction has some very desirable properties in terms of the knowledge soundness and the knowledge of it. And in general, the most important thing that we should take from this session is that state restoration is the natural thing to think about when you want to transform interactive proofs, to a non-interactive argument. And yeah, I encourage you to reflect a bit about that definition of state restoration and appreciate how related this definition is to this construction, 14.1. And of course, if you have any questions, feel free to write them on the channel. I'll try to answer those, and feel free to also email me or email us about any questions. And yeah, that's it, I think.
Awesome. Thanks.